All right, so lecture 25 is going to be a big, long example problem of an Otto cycle problem. So lecture 24 is just going to be the theory of air cycles behind the Deisel, or especially behind the Otto cycle, which we just talked about in parts 1 and 2, and then a quick discussion here in part 3 of the Deisel cycle. So this is going to be the last part we'll do, I think, for lecture 24. And then, like I say, lecture 25 will just be working through an example problem. Okay. Um, the Deisel cycle is an ideal model for what we call a compression ignition system, whereas the Otto cycle is for a spark ignition system where I've got an actual spark plug, a device that basically puts a spark into the air fuel mixture to cause it to begin the combustion process. In a diesel engine, in a diesel cycle, we actually compress the air fuel mixture up to a point and as to basically to a point where it blows itself up, right? It starts its own ignition. It starts its own explosion, basically. And that's what happens in a diesel engine. It's kind of this interesting thing. If you think about it this way, if I take a gaseous substance and I compress it, it gets hot as the pressure, as I squeeze it down, I'm going to increase the pressure, but I'm also going to increase the temperature. If you've ever used like a bicycle pump, the kind that you got the handle and you go up and down, and if you put a bunch of air into like a large like a lawnmower tire or something like that, or hopefully you've never had to really air up a car tire with one of those, but if you have, if you gently feel the bottom of that cylinder where you've been compressing air, it gets hot. It actually gets really hot. That's why I say carefully feel that because it can actually get pretty hot in some of those. So if I'm taking a gaseous substance and I compress it down, that temperature is going to increase. In a diesel engine, it's taking the air fuel mixture and it's compressing it down so much and getting it to such a high temperature that air fuel mixture actually blows itself up. Now we can do that with diesel fuel because it's very, very predictable and easy to control when that ignition occurs. We have to be much more careful trying to do that with something like gasoline because gasoline mixtures can vary too much. And so, really controlling when that explosion occurs on its own spontaneously is a little harder to predict with gasoline than it is with diesel. It's a very predictable phenomenon with diesel, so we can actually basically we don't really have to control it too hard. Just the parameters to control are actually pretty simple to control. All that to say, that's the basics of how a diesel engine works. And this is the diesel cycle. This is not necessarily a real diesel engine. This is not what it looks like in a real diesel engine. That's another discussion we won't have here. But this is the ideal reversible model that we would use to approximate what the diesel engine cycle might look like. So it's what we call a compression ignition. So instead of having where in the Otto cycle, remember from 2 to 3 was vertical, here it's actually horizontal. So the heat addition occurs at a constant pressure rather than a constant volume. Otherwise, it's much the same. Isentropic compression, heat addition, isentropic expansion, constant volume, heat rejection. Now, if we look at that, that means we've got an additional volume ratio. Remember, with the Otto cycle, we just had the ratio from max volume to min volume because there were only two volumes. There was volume from 2 to 3, and there was volume from 4 to 1 with the Otto cycle. So I just had a compression ratio describing those two volumes. Here I've got a third volume. I've got the volume at 0.3. So I have what we call the cutoff ratio. The cutoff ratio is the ratio basically during that heat addition process. It has a minimum value of 1. If it has a value of 1, that's basically an Otto cycle because that means it's constant volume from state 3 to 2, or 2 to 3, I should say. But this is the cutoff ratio. So it's another term we have to keep track of mathematically because the thermal efficiency for the diesel cycle looks like this. There's, in addition to the compression ratio, which still exists, that's the ratio of the max volume to the min volume. So that ratio still exists. But now I've got this cutoff ratio, which we just defined here is the volume change, or it describes the volume change during the heat addition process. So the thermal efficiency for a diesel engine looks like this. Now, the way we can increase this is if I can decrease that cutoff ratio, then basically that controls the size of this thing, this secondary term that's getting multiplied by the negative value here. Now, the same as we saw in the Otto cycle holds true. If I can increase the compression ratio, right? If I can increase the compression ratio, then that means I've got a bigger denominator on this negative quantity. That means I'm subtracting a smaller quantity from 100%. I increase the efficiency. But what happens is the cutoff ratio, the smaller it is, the smaller basically this term gets, right? The closer to 1 this term approaches. R sub C has a minimum value of 1, meaning this quantity will always be, this quantity in the parentheses will always be greater than 1. If you take your limits as RC approaches 1 and K is constant, this quantity will always be greater than 1. And no matter what K is. And so what happens then? Well, if you compare that, the efficiency for the Otto cycle, which looks like this, the diesel cycle looks almost the exact same, except you've got this term in the parentheses here. Remember, this term in the parentheses always has a value greater than 1. So I'm multiplying this negative quantity by something that's greater than 1, meaning I increase the size of this negative quantity, meaning I'm subtracting from 100% something that's larger than what I do with the Otto cycle, which screams at us that the diesel cycle is less efficient than the Otto cycle. And anybody that knows about engines and big vehicles knows, it's like, Steve, we use diesel because it's more efficient for bigger vehicles, right? And yes, something changes, something's different. Something's different for the diesel cycle, and it's because of the nature of the fuel. Remember, I said, how do we get the diesel cycle to go? We compress the fuel to the point where it blows itself up, meaning I have a higher compression ratio in a diesel engine than I do in a gasoline engine. So if I have the same compression, if I have the same compression ratio, the Otto cycle is actually more efficient at the same compression ratio. But because of the nature of the fuel, that diesel fuel, I can actually compress it to the point where it blows itself up, and that's very easy for us to predict. It's very easy for us to control. With a gasoline engine, it's not as easy to control that. And if I increase the compression ratio too much for a gasoline engine, it auto ignites. And as the rest of the cylinders in the engine are trying to push that cylinder up and get it to compress, and the explosion's already occurring and it's trying to push the cylinder out, bad things happen. And you get what we call auto ignition or pinging in a gasoline engine when that happens. Or in the worst case scenario, you blow ahead. You literally blow your engine out. In a gasoline powered engine, if it begins the combustion process while the cylinder is still trying to compress, that can permanently damage the engine. With a diesel engine, that doesn't happen. And the other thing is, in a gasoline engine, if you drive like a high performance sports car, and they'll tell you you only put the expensive gasoline in it, that's because it's running at a higher compression ratio. If you put the cheap stuff in, it might auto ignite while that thing's still trying to compress, and the gas is already blowing up, and bad things happen. Again, in a diesel engine, I can go ahead and increase that compression ratio because the fuel is a little more stable, a little more predictable, and I can get it all the way down to a smaller compressed volume before it begins to auto ignite. And then I can control that ignition process. And so that's the reason in practice, we can operate a diesel engine at a higher efficiency than what we see with a gasoline engine. Okay. All right. That is really good stuff. I'm going to stop there. And again, lecture 25 then is just going to be working through an Otto cycle example. We're not going to do any diesel cycle problems in this class for me. Otto cycle is far enough. Very rarely do we get to Rankine cycles. Maybe we'll talk about it a little bit, but normally in my class, I normally don't work problems. I try to focus on Otto cycle problems. So If you're in class with me, expect an Otto cycle problem on the final exam, unless I tell you otherwise, and we'll go from there. So like I said, it's going to be lecture 25. We'll work through an Otto cycle example, and my students have got some homework problems on that. All right, see you guys in the next one.